The objective today is to describe what a computer is and what computers can accomplish. So here's our table of contents. The first thing I need you to do is predict what a computer is. That way you can really take a moment to try to analyze what makes a thing a computer. And then I'll take a shot at it. After that, I'll add some details to the mix of what this thing is. Then I'll give you what I call the recipe for success. So when trying to define a computer, if you follow this like recipe or this checklist, you should be good to go. And then I'll try an overarching idea of what brings it all together. We'll do a quick activity and then a DOL. So here's your moment to predict. What do you think a computer is? Pause here and truly try to think about what makes a computer a computer. Trust me, this exercise will be good for your brain. And now you may listen to what I say a computer is. A computer is a device that performs calculations using a central processing unit. In the beginning of the year, we talk about how the word computer was used to describe people, a type of person who did a calculation. Today, we call those people nerds. I'm just kidding. So a computer is doing these calculations through something called a CPU. Now, you might not use this next term very often, but I'm sure it applies to many things in your possession. But the word microcomputer is interchangeable with the word computer. I read microcomputer in books all the time, and typically they're referring to just a regular computer, but I've just never heard anybody in like real life or in my line of work use the word microcomputer to describe anything like that. So I did a little research, and basically a microcomputer is something that's small enough and cheap enough to be dedicated to a single person. Now the CPU in a microcomputer is known as the microprocessor, and just like the other word, micro is often dropped, and you might just hear this thing called a processor. So here we go with synonyms. We have a CPU, which is sometimes this is referred to as the CPU, or it's referred to as the processor, or the microprocessor. All of these words typically mean the same thing. As if computer science wasn't hard enough to learn already, we're going to throw a ton of vocab at you. Thus, the reason we write so many think right shares in this class. So what this processor does is it performs the calculations or processing of the computer. Now, how does it do it? Well, an important invention that led to the miniaturization of computers was the IC, aka the integrated circuit. And these are often called chips. So when you see something that looks like this or this is a chip. Now, oftentimes what's inside a chip is a series of what's known as logic gates. And these are created out of transistors. And a lot of times when you see IC, like integrated circuits, you'll see them on this PCB board, which of course has these little electrical connections that go to different places, and many computers are made up of several microchips. So there are a handful of basic building blocks for any circuit. You have your resistors, your capacitors, your inductors, and transistors. Now an integrated circuit, as you'd have seen it in the 1970s, would consist of 10 to 30 transistors and less than 5 each in terms of resistors and capacitors. Now today, due to the advances in technology, the number of transistors can be in the millions or even billions in some of the really advanced chips. Now the way I like to remember what an integrated circuit is I flip the word around and mash up the ending. So an integrated circuit is actually just circuits inside this little black thing with the silver pins. And if you're a kinesthetic learner using your hands, just think of the circuits inside of this chip. Really get into the interior, you would need a microscope so you could see this happening. Now, you won't really see lines in this way. This is an electrical schematic of what's inside this chip. If we go to this view, here is actually what you would be seeing inside using an electron microscope, which is mind-blowing to think that all of this is somehow creating something we see on a monitor. And now technology is advancing so much that you'll have something really thin like this doing the job of something clunky like this and doing a better job at it. So more on integrated circuits later. For now, just know that the most magical component of them all is the transistor. And for now, just think of the transistor as a switch, like a light switch in your house. Now, an individual transistor is not so interesting, but what we can build with them, with many of them, is amazing. Almost unlimited. I mean, artificial intelligence coming from a bunch of these is pretty mind-blowing. Now, we're not building computers with these types of transistors. We're using some microscopic ones, or at least some really tiny ones. But when I think of a transistor, I think of this because at the end of the day, it's just a switch. You have two things connected, and the thing in the middle can either complete the circuit or turn off the circuit, or, you know what I mean, disconnect the piece that connects these other two pieces. And then think about memory. How can a computer store something? If a computer uses electricity, how can we keep electricity going even when the computer is turned off, even when the battery is pulled out? And so I wish you could see this in action, but this is what's called a flip-flop. So using an OR gate is as long as there's one input on, the output will be on. So in this situation, there was an on over here, so this is on, and it comes down here. And so thus this turns on, so it goes up here and turns this on, which turns this on, and so on. But the challenging question here I want you to try to answer is, does a computer need this concept of memory to be considered a computer? Okay, so let's go with this checklist of what has to happen for a thing to be a computer. The first one is it has to take input somehow. The second is it stores that input, so even if it's temporarily, I'm going to say it counts. Third thing that needs to happen is it processes that input, so a light switch isn't a computer. You just turn the switch on and the light stays on. It's not taking any more new input. I figure a direct correlation like a 1-to-1 does not count. So the input of flipping the switch on, turn the light on, but if there's no other input outside of that, let's not call it a computer. And the fourth thing that needs to happen somehow is an output. So as long as we have those four things, we have a computer. You'll be surprised to know some of the first computers were made of wood and metal. So technically speaking, we don't even need electricity. Now it's going to be huge and clunky, but it can still be considered a computer. Now there's this video on studio.code.org, and then you can fill out the rest to get to it. But they do another good kinesthetic movement for my motion learners out there. So I'll play just that one small part so you can see the movements. So to put my own touch on it, you take input in and you store it in your heart because everybody has their feelings first. Then it goes to your mind for processing, and then there's an output. Now if you're really interested in these old wooden machines and metal computers, there's a book called The Difference Engine, and a lot of people consider it the first steampunk book out there. But William Gibson is a terrific writer, and if you're into that kind of fiction, you might want to check it out. So let's see if you can do this without looking. What's the checklist? What's the four things that need to exist for something to be considered a computer? Now let me give you a little more details in terms of step 1 and 4. So that's the input and output. All interaction with a computer has to take in some sort of input. So examples would be keyboard, pointing device, scanner, touchscreen, etc. Then output devices such as display, printer, a storage device, that even counts. So I'm talking like long-term storage, like a hard disk would count as well. Or a network adapter, something that sends your input long distances to another computer or another person's phone. This can also be considered an output. So how does all this happen? Well, the motherboard. So if you're unfamiliar with the term, I wanted to introduce it to you now. The motherboard is the central computer circuit board where all the components are connecting. So the projector or the monitor is connecting the other pieces, the CPU and the processor, and the short-term memory like RAM, and the long-term memory like a hard drive. Now, these are some things we won't be covering today. I just mentioned RAM. There's also the firmware on a circuit board. This is the software for all those integrated circuits. Thus the word firmware. It's in between software and hardware. But there's also something called ROM BIOS, which has recently been replaced by UEFI. If you're just dying to know more, I would definitely Google all four of these terms. Another thing we should be mindful of is when people say computer, there's basically two types of computers out there. There's a server, and this is doing all the same things a computer does, but it's definitely serving other computers. So in that sense, that's why it's called a server. So it's serving other clients. Now the client is typically your home computer or your cell phone. That is thus using services on a server. Okay, so here's our activity for the day. It says the Internet of Things describes the wide array of devices that previously did not contain microcomputers, but now do and are connected to networks. An incomplete list includes kitchen appliances, thermostats, utility meters, components in automobiles, light bulbs, and industrial control devices. So I want you to choose 3 of the items from the list above and detail how the 4 requirements on the computer checklist are met. So here's my example. I'm going with a kitchen appliance, such as a coffee pot. So a coffee pot can take in my input, such as the time I'd like for it to start. It'll process that number with the system's clock, and then output the coffee at the correct time. But now that I've written out my thoughts, I'm thinking, wait a minute, I forgot about the storage part. I don't know if it's storing anything, so maybe the time I gave it can count? Well, it's okay to feel unsure at the end of your choices here. This is a good example of an answer I'd still like from you, even if you feel like you've found a non-example. Non-examples are still helpful to learning. Remember, I'm giving you credit for trying, always. If you really get stuck and you want to do some typing, you could type out this URL and get some examples, other examples besides this one I gave you now. So now that you're done with the activity, I will give you one challenge question and then we're pretty much done for the day. Before I do that, I thought I should show you that I made my own IoT coffee pot at home here. Well, just kidding. I found this picture on the internet and thought it was cool. And I also found this picture on the internet and thought it was crazy. It says coffee by drone. If this person started a company, and I hope they have hired a lawyer. If any of you feel like it, you may bring me coffee in class, but not via drone. So here's my challenge question, totally optional. I want you to think, is this Starbucks button a computer? You basically program in your favorite drink, and all you have to do is push the button when you're near a Starbucks, and your order will be served for you. So we're at the end of the lesson. What did today's lesson remind you of in terms of an IB attribute? Would a lesson like this mean that you're a reflective person, a principled person, an inquirer? And now that you're done with that, a pretty simple DOL. You're just picking these things to help you describe what makes a computer, so what qualifies as a computer. And you just take the number and connect it to the letter for the corresponding description. So here's my example. I can't really give you a really good example or else I'd be giving answers away. But let's say 1 right here, connected with the definition of D. So all you have to do is write 1D and do it for 2, 3, and 4, and you're all done.